Yes, sir.
I'd like to go first.
Your group would like to go first, mostly because you're going to have your significant other here to observe.
No, mostly so I can shoot myself in the foot at the beginning and then be done.
Okay. Reviewing for the final exam, because this is our last calculus specific.
This is exam 4.
Okay, well, that's just a mistake. There we go. It says final exam. This is our last calculus specific class period. In this class period, we've been looking at the calculus related things of what we talked about in the other meetings. And so for our final exam, you'll have 2 calculus based questions. One will be on this material here, and one will be from the material all semester long. So I'm going to review what we've just done. And then for the other material, go back and look at what we did in the preceding that were the calculus things. So just look at the review exams I gave before each exam. And actually the last 2 didn't have calculus questions on it, so it'd just be the first 2. So here is, in short, the things that you could have. Lorentz transformations, that was going through, and what I would give you would be the calculus part of that actually, where you find the equation for either parallel or perpendicular addition of velocities using the Lorentz transformations. So that's what the second line says, the relativistic addition of velocity. And then the quantum mechanics that we've been covering for the last 2.5 lectures in this class period. So looking at the review, we had space-time invariance. There's one that we introduced here that was a space-time invariant. Do you remember what the space-time invariant was here? It's kind of tricky.
It's not time.
It's not time, it's not distance, and it's not r. Which, of course, is all of the variables you see here.
Yeah.
Speed of light.
It's actually not the speed of light, although that is a space-time invariant. But it's not the one here. It is on the screen.
It's
Relativistic space-time.
X.
Okay,
CT.
it is, I know, this, it is this. That's the space-time invariant. Now, okay, there. The 0, the radius minus radius, or radius squared minus radius squared actually is what that was, is the space-time invariant. And no, I'm not going to ask you what the space-time invariant was, but that was one of our space-time invariants, which we got from saying the radius for light moving out from a point can be calculated using time, radius is equal to ct, or using Pythagorean theorem, radius is square root of x squared plus y squared plus z squared. So we did radius minus radius is 0, and that was a space-time invariant. In all reference frames, that's going to be 0. I was thinking, well, this looks fuzzy. What are you talking about? But it's actually the picture. It's out of focus. So using that, we were able to get the calculations for Lorentz transformations. So these here are the Lorentz transformations. And those equations would be given on the test. So you don't have to go memorize them. But then we have to take those and use them. That's what you might have to do. So how do you use those to find addition of velocity? Do you remember the process, the steps? Probably should take that as a no then, huh? So our steps were first, make sure we define u is equal to the speed of an object. And so ux equals speed of object in x direction in the unprimed frame. Thus, dx dt for that object. And ux prime would be the speed of object in x direction in primed frame. So that would be dx prime dt prime. Notice the primes are on both of those. And so what we're trying to do is to find a relationship between these two. That's for finding parallel velocities, because we always use v in x direction to make life easy. So if I'm finding ux in terms of ux, the relationship between ux and ux prime, then it's parallel velocity. If I'm trying to find like uy in terms of uy prime, then that would be perpendicular because y is perpendicular to x. So the first step is just to make sure I have these definitions. The second, so that was one. The second step is use Lorentz transformations to get those variables in terms of t, so that I would have ux prime is equal to d, and using the x prime equation, that's gamma x1 minus beta ct. Right, that's, oh, actually, I put x0, but x0 is ct. Actually, you can't use beta ct because, well, no, you can. Yeah, you can because that's what it is. And it's going to be over d, and then for t prime, I'll take this equation, and remembering that x prime is, or excuse me, x0 is, okay, I did this backward. This here should have been the thing on bottom. I took the equation for x0. X0 is the ct prime. So that should have been gamma over c, gamma over c, so I have time instead of ct on the left side, times that should have been on bottom. The top is x1, and so x1 prime is gamma. Seriously? I did do it right the first time. Guys, I am insane today. Okay, so on bottom, it's x0 minus beta x1. So ct minus beta x1. Okay, so it took me 3-4 tries. On top, it's x1 minus beta ct. Yeah. So then we have that substitution. Now everything is in terms of the unprimed variables. But we still have one last step to go. Step 3. Make each derivative in terms of dt. So that means I'm going to make this dt and dt. So I took the top one and made it dd, with respect to time, bottom one with respect to time. And then x1 dt, well, that would just be dx dt. And dt is just 1. Likewise in the bottom. So doing those substitutions, have, and now we zoom so I can write it and have it so it comes out, right? Notice the gammas now are going to cancel. And since this is 1 over C on bottom, I'm just going to, I'm going to leave the top as it is and bring this 1 over C inside of that parenthesis. So on top I have ux, because that's what dx dt is, minus v over c times c minus v over c squared times ux. And so there we have the equation for addition of velocities derived using the Lorentz transforms. This was for parallel velocities. So if I was going to do perpendicular, what would be different? I'm not going to do the perpendicular right now because I made enough mistakes with the parallel. What would be different doing the perpendicular?
Would it be uy instead of ux?
You're not the bottom. The bottom, the denominator stays exactly the same because that was the dt prime. But the top is going to be dy. But if you look at y prime, that's x2. x2 prime is just x2. So the bottom's going to stay exactly the same, and the top is just going to be uy. And so if you do addition of perpendicular velocity, the top is just uy. You don't have the gamma divided out, so you're going to have a gamma out front, and then everything's the same in the denominator. So you're going to have ux and uy for the perpendicular velocity addition. So it's a pretty straightforward thing. If you know how to do the first one, you can definitely do the second one because it's easier. Any questions about the perpendicular velocity addition or the parallel velocity addition? So, yes, I had another page where I had rewritten the Lorentz transforms. What's the difference in these Lorentz transforms? These here are written dividing everything by the c's. So instead of having x0, which is ct, you have just t. So that's the only difference. They're equivalent. And so here are the resulting answers. That is going from the unprimed to the prime. This is going from the prime to the unprimed. What's the difference in the two? The only difference is the reference frame for v. Frame 1 sees the particle going away at speed v, so frame 2 sees the particle approaching at speed v, or sees frame 1 approaching at speed v. So the sign of the v is shifted. That's the only difference between those two equations. The sign of v is shifted. So if you can do one, you've already done the other. Because what was special about the prime? Nothing. We just chose one reference frame and called the other one prime. Okay, so that's the relativity part that you could have on your exam. Then the particle in the box, the quantum mechanics part you could have. So the particle in the box, you might be just asked about technique. You might not have to do any calculus because this here is a rather complicated thing. You have to have calculus to do it, which is why it only came up if this was calculus class. But actually doing the calculus is oftentimes pretty difficult. So we start with, for a particle in a box, we have a prescribed potential energy situation. And you're only going to be looking at particle box. I'm not going to give you some other random thing and say, aha, what you have here now. Now, for Chad, I could do that. In fact, he kind of wishes maybe I could do something like this for calculus, or not for calculus, but for quantum mechanics. So you have a prescribed potential energy function, and then you put that into the Schrodinger equation. The Schrodinger equation is just an energy balance equation. It says the total energy E is equal to the kinetic energy, which you get by putting this here, which is the calculus or the quantum mechanics way of saying momentum squared over 2m, kinetic energy, times psi, plus the potential energy times psi. So energy times psi plus kinetic energy times psi, or equals kinetic energy times psi plus potential energy times psi. It's just an energy balance. It's an important thing to understand. The Schrodinger equation it's just an energy balance equation. And then you solve this equation. So once we know what V is, then we solve this equation. So in our case, we had three regions, region 1, region 2, and region 3. And so we solve that equation in each region. In regions 1 and 3, V of x is infinite, which the equation can only be true since the energy, you're not going to have an infinite energy particle. Then the only way you can have this true, have a finite thing on the left and an infinite thing on the right, is if psi is 0. So the solution has to be 0 in regions 1 and 3. We went through and looked at it with calculus, but logically you can answer without doing calculus. It's going to have to be 0 in regions 1 and 3. You're left then with region 2. And so in region 2, this V was 0 and life was a little easier. We just had a simple second order linear differential equation. And I had to tell you that the solution to this has the form psi is equal to e to the bx. So likewise, if I were to give this on the exam, I would tell you the form of the solution is psi is equal to e to the bx. Find psi. Now, if you put e to the bx, you don't get any credit. That's not the answer. That's the form of the answer. So what do you have to do then? Take the what? Not in this case. I understand if I want to solve it for x, that's what I would have to do. But what I'm trying to do is actually solve for what psi really is. And so I have to take the second derivative because I have the second derivative here. Now, what does this funny shaped D mean? Partial. You guys have studied those now, right? So we're going to take that partial second derivative. Well, the truth is, by the time I got to this, there's only one variable in psi. We've separated out the time-dependent part from the time-independent, and so those can be regular derivatives. There's no difference in a partial or regular derivative if you only have one variable. So it doesn't matter. It can be written either way when you get to the time-independent Schrodinger equation, and thus usually it's written without partials. Usually it's written with exacts like this because there's only one variable. So if I take the second derivative, what's the second derivative of psi here? With respect to x. What's the first derivative?
X.
Okay, it's actually b, e to the bx, right? You bring down the derivative of the exponent. I know you were thinking the right way. You just said the wrong one. So second derivative, bring down another b, and that's b squared e to the bx, or if you prefer, b squared psi. So then you just put that in and you have E psi is equal to minus h bar squared over 2m times b squared psi. So you rearrange that. So you have E plus h bar squared b squared over 2m. Come on, stop that. Psi equals 0. Now there's two reasonable solutions to that. What are the two reasonable solutions? Solution number one,
Trivial
The trivial one, that's right. You can never in your calculus classes forget that it exists. Your teacher might mark you wrong. But at the same time, you're never going to use it because it's the trivial solution. If we have psi is equal to 0, our trivial solution, then our result is, so there's no particle in the box after all. But we said it's the particle in the box problem, not the no particle in the box problem. So we can't set psi equal to 0. We can't go with that trivial solution. So instead, we say this thing in parentheses has to be 0. And so that demands then
Is it a plus? E plus?
excuse me?
Is it an E plus?
So yeah.
Yes, that's a plus sign. Therefore, b squared is equal to, we usually put the e after the 2m. I start writing things out just in the order that makes sense to me, and then I look at the answer and I'm like, well, that's not the way everyone writes it every time. This is the way everyone writes it every time. So b squared is minus 2me over h bar squared. Well, how do I get b from this? A very trivial question, not a tricky one. How do I get b? But when I do the square root, there is the tricky thing. What's that? You end up with two answers. Plus or minus then we have another thing. Since potential energy is 0 and kinetic energy is always positive, E is going to have to be positive. And so I have E is positive, M is positive, H bar is positive, a square root of a negative value. So what do we do when we have square roots of negative values? I was hoping somebody would say, we run around and panic.
I can do that.
I get that better, yeah.
But the correct answer was I. I mean, just think back when you were like in 5th grade. They just told you does not exist. But now we have this imaginary number I, and we say it exists. And so what we found is B is equal to plus or minus IK, where K is defined as square root of 2ME over H bar squared. And you are free to ask, why did we introduce K? We didn't need to. Why did we do it? Yes. I would say physicists are lazy, but it's not lazy. It's we want to be efficient. And I said, we want to be efficient in our writing. We don't want to write out long equations when we can make it shorter. And so we just use this K. So we actually have two solutions to finish this page. We have psi plus psi plus is equal to E to the IK, and psi minus equals E to the minus IK. With those two solutions, then our overall solution must be the linear combination of the two, adding these two together with some constant in front of each one. And so our solution is going to be in region 2, psi subscript 2 equals A e to the IKX plus B e to the minus IKX. Is that ringing bells? Kind of like when you get punched in the head, right? You've had worse. The car accident was worse.
Don't wait, that's in my slides.
Is it?
Yeah, because I talked about magnetic imaging.
And they found you had a brain, right?
After they took my blood.
It's always a relief to find these things. Found I had a heart, had some problems, but it was there. We then use the Euler relation to write this as a sinusoid. Sometimes you do, sometimes you don't. So those two things, the black form and the red form, are exactly equivalent solutions. The one on the right is using the Euler relation that e to the I theta is equal to cosine theta plus I sine theta. Yeah.
In the D sine, is that a K?
That's a K, yes, that's K. In my mind, that's a perfectly legible K.
That looks like LDX.
It does. That's a K. That's a K. Better? Let's make this look more like an X instead of a backward Y as well. Okay, so we have solutions. Do we have a quantized solution?
Since you asked the question, I'm going to say no.
That's a good analysis. Since I asked the question, it's no. We don't have yet because we don't have values of anything. It's still continuous. So how do we get quantized system? We apply the BC, not before Christ in this case. Boundary conditions. That's where the quantization occurred, when we apply the boundary conditions. If you don't have any boundaries, it's not quantized. If you have a free particle, a particle that doesn't have any boundaries, it's not quantized. It can have any possible, or any, I say any possible, quantized can have any possible, only these are possible. It can have any at all energy. But if you have boundaries, then it's going to quantize it. So now we have to go to the boundary conditions. And so here is summarizing the outcomes that we just did.
So I have a question.
Go ahead.
Since we can obviously see from the picture, aren't the boundary conditions just 0 and L?
The boundaries are 0 and L.
Okay. Yep. Now I understand.
The boundary conditions are shown right here. The wave function is continuous at the boundary. And in all cases except for this one, you also have a second boundary condition that says that the derivative of the wave function is continuous. If we have an infinite boundary, then it's different. And so the first one we teach you has a different boundary condition than all the other problems you ever have in quantum physics. It's just simpler. That's why it's the first one. It's not trying to lie to you. It's just a simpler form or a simpler condition. So we apply our boundary conditions. So I'm going to use my solution of the sinusoids because I know it's easier. How do I know it's easier? Because I've done the problem before. So sometimes there's hindsight that comes into this. You can do it either way. I am not going to give you a problem that has you go from beginning to end. I could give you a problem that says find what the wave function is, but don't apply boundary conditions. Or I can say this is the wave function that you get from the Schrodinger equation, apply the boundary conditions. But I'm not going to have you do the whole way through. Just, time. It's not what you have an infinite amount of on a test. So applying the boundary conditions at x equals 0, psi Roman numeral 1 of 0 equals psi Roman numeral 2 of 0. Well, we had already identified that psi 1 was equal to 0 and psi 3 was equal to 0. That's a 3. I don't know how many vertical lines I have to get 3 that aren't on top of each other.
I guess 2.
Okay, there it is. So we already had those, and then we had psi in region 2 was equal to c cosine of kx plus d sine of kx, where k was equal to the square root of 2me over h bar squared. When I was actually even starting out as a teacher, I would often forget what my k was and go looking for it. Well, I got that in my Schrodinger equation work. It's not like you should have to go looking for it if you really know what you're doing, because It came out from our definition right here. So looking at that boundary condition, this is 0 for psi 1. So psi 2 is c cosine. If x is 0, then kx is 0, plus d sine of 0. And tell me, what is cosine of 0?
1,
What is sine of 0?
0.
Okay, you're totally on top of that, Trace.
Ooh.
So this is just equal to c. So 0 equals c. Well, that simplifies life. After applying the first of our two boundaries, I now know that I can simplify my psi 2. I can simplify my psi 2 to psi 2 equals d sine of kx, because c was 0. So now I go to my second boundary. It's not quantized yet, right? I applied one boundary, still not quantized. Psi 2 at L is equal to psi 3 at L. Well, psi 3 is 0. Psi 2 is d sine of k times x, which is L at the boundary. Now I have d sine of KL equals 0, and boom, quantization occurs. Because if d is 0, what do I have? I have the trivial solution again. So we automatically say that can't be the answer. So the answer has to be sine of KL is 0. And sine is 0 every time KL is an integer multiple of pi. So this gives us a condition that KL must be equal to an integer multiple of pi. And if KL is equal to an integer multiple of pi, since we know K is the square root of 2me over h bar squared, then I can solve for E. And I have now it's quantized because n, where n equals 1, 2, 3, etc., any positive integer, why is n not equal to 0? It's again trivial solution if n is 0, because you'd have sine of kx is always 0 if k is 0. Why is n positive values? Well, we had plus k and minus k already. If we allow n to be negative, we're just duplicating our solutions. So that's why the n is only positive integers. And so I write an E with a subscript of n here to indicate, yes, it's now a quantized energy. These are the energy values available where n can be 1, 2, 3, 4, 5. So now I have quantized energies. So this would be basically what we did on this slide could be a problem on the test, or what we did on this slide could be a problem on the test. Or, we're not done yet.
Could both of those be on the test?
They won't both be on the test, no. Just because of the time issue. Now that we have the energy, the quantized energy, we go back to the psi. We have psi sub n is equal to d sine of, and I'm going to go ahead and put this as k to make my, well, k is equal to n pi over L, so I'm going to put n pi over L. That's by far the easiest way of writing it. So there's my psi. So what do I do with these? There's a third possible problem here. Actually, there's more than a third. There's a fourth. One thing we need to do is find what this value is. Now, I know I have A here and I had D on the preceding slide, but they're both constants. So how do you find that? You apply normalization. Normalization is if I sum the probability find the particle at every location, I should get 1 if I have one particle. Right? I can't have a single particle and it has a 70% chance of being here and a 70% chance of being here. That just doesn't work out. It has to be, 50-50, 30-70 if it's only 2 positions possible. Well, here we have a continuous distribution, and remember, our probability density, our probability per unit distance was probability dx is equal to psi mod squared dx. So if I add these up over all space, which if it's a continuous function, that means integrate over all space, that has to equal 1. The addition of my probabilities, integral because it's continuous, over all space has to be 1. And so we can take this and say, aha, that means the integral of, and I'll stick with my d star sine of n pi over Lx times d sine of n pi over Lx dx has to be 1. What are my limits here if I'm going over all space? It's kind of a tricky question.
Well, I'm assuming the compound's going to be infinity.
It would be, except for this was only psi 2, right? Psi 1 and psi 3 were zeros.
So this is 0 to L.
That's right. This is only 0 to L because it's really the integral from minus infinity to 0 of psi 1 mod squared, which is just 0, plus the integral from 0 to L of psi 2 mod squared, plus the integral from L to infinity of psi 3 mod squared, which is once again, psi 3 is just 0. Chad had a question.
So if we integrate from 0 to L, what about the chance of this particle tunneling past?
Because we have an infinite barrier that doesn't have it has an infinite thickness as well, then there is no tunneling possibility. Right? If it was of a finite thickness, then it would. And I don't think we talked about tunneling with them. We probably should have. It was in my last slide. Okay. It was in my last slide, I think, from what we talked about last week, but I don't think I talked about it carefully here. If I did, well, it's not going to be on the test. So we do this integral. So I have d mod squared times integral from 0 to L of sine squared of n pi over Lx dx is equal to 1. And yes, that's a d. I'm just going to rewrite it. That's d. So we have to do that integral. Integral of sine squared is not so hard. The easiest way, like I said, is to recognize that sine squared is equal to 1/2 of 1 minus cosine of 2n pi over L, or 2n pi x over L. And when you do the integral over 0 to L, a sinusoid, whether it's sine or cosine, going from through 1 cycle or 2 cycles or 3 cycles, it's always going to give you 0. So really, you have the integral of 1/2 from 0 to L. Which is pretty simply d mod squared times L over 2. And so that gives us a value for d and you are free to tell me I made a mistake.
Yeah. Why did you switch them?
Well, I had 1 equals here. So I multiplied by 2 and divided by L. And then I square rooted. Okay, I didn't write the plus or minus. I didn't write the plus or minus because there are actually an infinite number of values I could have, because I could have times any phase factor between real and complex. And plus and minus are just 2 phase factors. And we have to just choose one. Why not choose the real one? And so I just chose the real positive phase factor and went with it. So If you want it to be all kinds of crazy, you'd have times e to the I a, where a could be any value. There's an infinite number of solutions because a could be any value. But why worry about it? Let's just choose the value where a is 0. And so that's why I just chose it with the plus sign. Okay, so this is the normalization constant. So now I have a more complete wave function. That is the complete wave function now. So this is called normalization. What I did here, I could ask you to normalize it. And so you would have to go through the work and you would have to actually, both times we did this, I didn't look it up. I just said sine squared n pi over Lx has to be this. I tried to remember, I would probably actually give you a table of trigonometric identities so you could do that. So we've normalized it. So we found only two more things. We have what is the expectation value for position and for energy. And you're like, the expectation value? What's the expectation value? The expectation value means the average result I would get if I did a whole bunch of measurements. So where do you expect the expectation value to be if I have a particle in the box?
A single one? So wouldn't this follow the n equals 1 path then?
Well, if it's a particle in the box, no, n is not the particles, n is the energy state. But if I have a particle in the box, knowing nothing else, where would you expect the average position to be? Take a whole bunch of measurements of this position, where do you expect it to be? Center. At the center, right? That's pretty common sense. And it turns out that's the correct answer. But on the test, if I said, what is the expectation value for position, and you just put the center, I would say, hey, good try. Thanks for writing something down. Because you have to actually show how you get there. So the expectation value is found by doing, no space here, and I have to insert a page here. I've been actually doing a good job, generally speaking, with my page spacing today, up until now. I only put in one page, which is probably a poor choice of mine. The expectation value is written like this. And that's the integral over all space of psi star x psi dx. So in our case, because we now know psi is square root of L over 2 sine kx, that's going to be the integral square root of L over 2 square that, or excuse me, square root of 2 over L, square that, and it's 2 over L. I'll put it out front because it's constant. Sine n pi x over L times sine n pi x over L is sine squared n pi x over L. But then we have the additional x dx. So it's a different integral. And we're just going from 0 to L because it would be 0 integrated from minus infinity to 0, and then 0 integrated from L to plus infinity. So then we actually have to evaluate that integral, which is a harder integral to evaluate. Once again, I would have to give you some integral table stuff for you to be able to do it. Actually, now that I think about what I would give you is just the integral of sine squared dx is this, integral sine squared x dx is this, integral sine, and so on. Just giving you those different options. You basically have to, this is the one that my integral is, so there's the answer. So you would have to do this, and it does turn out that it gives you L over 2 regardless of the n value. So integral table is what is missing here.
What about the extra x?
That's what makes this different than what we had before.
Because L over 2 came out to 4.
Actually, what we did before was, yes, it was L over 2. You're right.
So,
But this was 2 over L times this stuff. So what it's going to come out to is 2 over L times L squared over 4 is what that integral is going to have to come out to. So that comes out to L over 2. I mean, I know what the answer is. So I'm working backward to write that that's what the integral comes to. You would actually have to show how you did the integral, just saying using the integral table, blah, blah, blah. So there we found the expectation value, the position you would expect to find it if you did an infinite number of measurements. I had on this also, what's the expectation value for energy? That's a trick question. It's a trick question because what did we find? We already found these steady state energies. You can be in state n equals 1, where you have a 100% chance of being in energy E1. Or energy state 2, where you have a 100% chance of being in energy state 2. So that's kind of a trick question. If you're in state 1, it's 100% going to be this. If you're in state 2, it's 100%. There's no fuzziness. It's exact. Whereas the position, there's a fuzziness. Every time you measure position, it's going to be a different location. And you just found the average for the expectation value. Now, the final thing here, which is good because I have 3 minutes. I actually timed this lecture real well. You got to end this class on one good, The final thing is, I said that the probability is psi squared dx. Well, probability. So if I take those wave functions, the blue line for n equals 1, the red line for n equals 2, the green line for n equals 3, the black line for n equals 4, and I square them, then that tells me the probability of finding the particle at each location. And so I can take the lower one, the n equals 1, square that, and I'm just going to have something that goes like this. Where is it most likely to be found? You can look at it without doing the calculus and say, well, that's clearly most probably going to be in the middle. And because it's symmetric, my expectation value is also going to be in the middle. So you can visually make that connection. Now, if it's in n equals 2, when I square that, I'm going to have something that has 2 humps. So I have 2 locations where it's equally probable, most probable. Because it's still symmetric about the center, my average position is still going to be the center. So you can tell by looking at it, if you square it, you're like, without doing in calculus, I know if I square this function, its average positions at the center. And so you should be able to look at psi, do a square of it, and be able to interpret what that means. We have a lot of stuff here on the calculus, on the quantum mechanics. We've been covering it for the last 2.5 weeks of lecture, so that's understandable why it's more. Any questions about our review here?
So if we had an n equals 2, and we got to that point and you asked us what it could be, and we said the middle, would we also have to express that that is the, like, it cannot actually be in the middle, even though that's what it theoretically says?
Well, it doesn't say it's at the middle. It says it cannot be at the middle, but if you take a bunch of measurements, the average position is at the middle. So the average position is at a location that can't exist.
So if we got to that point, that anyone wants to put that down?
Yeah, I would like to see some knowledge about that, yeah, which you have. All right. I'll see you for lab in an hour and a half. Except for Chad, because I'll see Chad.